All right. Okay. Work, please work. You want a desk? You can sit next to Amanda. Too far. Okay. So, not this one. This one. What I have here is an observer. I represented the observer by a little dot. Sometimes you'll see the observer as a little eyeball. Today it's going to be a little dot. I have my object, which is not a dot. Sorry, two-dimensional object. It's got a size to it. And I have my mirror here. And normally in diagrams, to draw a mirror, you should indicate which side is the shiny side. I didn't do that because it's the PowerPoint, but I'm going to show you now. Let me just fix this real quick. So here's the mirror. And when I draw a mirror like this, the shiny part of the mirror is this side. That means there's going to be a reflection on this mirror. Now, the first thing that you need to do, step one, is draw the image. Already, Jan? We're done? Step one, draw the image. Now, we kind of know where that image is going to be. Someone have a guess where that is? Yeah, Max? You're right, it's the same distance. What's the distance right now? So this is not the most simple problem. I decided to skip over the most simple one and give you a second level question. You can call it that, but in fact, if you were to extend the mirror, all right, this object is going to produce an image exactly flipped an opposite side on the other side of the virtual mirror. That is extended mirror. Okay? But there is no real extended mirror. So we're going to actually have to draw a ray diagram to figure out where the image is. Okay. So this object, we're going to assume instead of it being made of a line, which is a line is made up of how many dots? An infinite number of dots, right? But really the most important dots are the first one and the last one, because everything else in between is going to be predictable. So let's break this object up into two dots, right? Beginning dot and an end dot. And all objects that have that that you can see, they emit light. They either emit it themselves, if they're a light bulb, it's emitting light, or they reflect light which they receive. So for example, this object got its light because the light came to it, and now it's going everywhere. Everyone around it can see it. Whether you're standing here, there, or there, you can see this back. So that means this object is emitting light in all directions. So let me just draw a couple of them. There's light going in that direction, that direction, that direction, that direction, that direction, that direction. Okay? Some of these are going to hit the mirror. Let's draw a few of them that hit the mirror. All right? It doesn't matter which ones you draw. Just draw any of them that hits the mirror. Let's draw three. Ideally, they would be straight, not like mine. Okay? Are these incident rays or reflected rays? Yeah, they're incident because they're coming from the object. It hasn't touched the mirror yet. When an incident ray hits a mirror, what happens to it? It gets reflects. Which angle? Same angle. So let's draw a normal line for each of these rays. There you go. All right. And so the angle that this incident ray creates with the normal line, right, has to be the same angle for the reflected ray on the opposite side of the normal line. So here's the incident angle that I just drew here. All right, so this angle here, incident angle. So that means there's going to be a reflected angle on the other side of the normal line with the same value. See that? Okay. Okay. So hopefully you get that this angle is equal to this angle here is equal to this angle. And now are these still incident rays or are they now called reflected rays? No, they're reflected. They hit a mirror, they're reflected. How do we draw an image again? It's where what rays meet. What kind of rays need to meet in order to form an image? Yeah, the reflected rays, when they meet, they form an image. So let's find out where the image of this dot is made. So here's all my reflected rays. Look, they're converging somewhere over there. That's pretty good. Let's work backwards and find that. My drawing sucks. I'm going to cheat. There they are. They meet over there. Whatever. If you work backwards and you use a ruler, this should be no problem. The reason I'm not getting it is because I'm not using a ruler. And it should be at exactly the same distance on the other side of the mirror. In fact, I'm so sure that another way of drawing the image would have just been to take the perpendicular distance to this dotted line and draw the image on the opposite side at the same distance. You would get the image perfectly as well. Okay? You have to use a protractor this way. It's a bit more complicated, but this is actually what's happening physically for that image to be produced. Okay? So now I've figured out where my image is. I would theoretically do the same thing with the other dots. I don't want to make this too messy. I'm just going to draw it roughly there and say that this is now my image. An arrow that's pointing inwards towards the mirror. Is it real or virtual? Virtual. Because remember, in a mirror, images aren't supposed to be formed behind the mirror. They're supposed to be formed in front of the mirror if it wants to be a real image. So in this case, it's a virtual image because it's formed behind the mirror. And that has nothing to do with the observer yet. The observer hasn't seen anything yet. This is just where the image is being formed. Whether the observer is here, 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 anywhere, that image is there regardless. Okay? That's where the image is, no matter what. I need to erase this, so I need everyone to be on the same page. Now we're good. A couple more seconds for you to finish up. So step one, done. Step two is going to be to draw the rays from the image to the observer. Step two. So I'm going to erase this and we're going to start with that process there. All right, so all I have is my image now. Oops. That's going to take a second to erase. So now I have my image where it's supposed to be, and I have to draw the lines directly to the observer. All right, so there are two important points, the frontmost and the backmost, so we're going to draw one for each. Please, please, please erase. So we're just going to ignore it. All right, so there's one ray going from the tip of that object to the observer, and the second ray doing the same thing. Oh boy, it's very hard to draw a straight line on it. There you go. Like that. Are these rays incident or reflected? I have both answers, so which one's the correct answer? Let's get some other answers. What do you think? Reflected? Someone else on that table? What do you guys think? Reflected or incident ray? Reflected? What do you guys think? Reflected. It is reflected, not because it's the popular answer. It's reflected because it's coming out of a mirror, okay? Or it's coming out of an image. The image is only there because of a reflection, right? So these are going to be considered incident rays. And so sorry, reflected rays, not incident. I'm going to draw a normal line where those rays, right? And just because I have uh, now that I have the reflected ray, I can work backwards to find my incident range. It doesn't just go in one direction. If R is equal to I, then I is also equal to R. So I can figure out what my incident angle is. It is an angle for one of them. Nope. Oh, like that. Like that. So step 3 would have been to work out incident ray back to the observer, back to the object. Any questions on that? Okay. All right. That was a simple question. Let's complicate it a little bit. Not that much, just a little bit. Can I go on to the next slide? Anyone say no? Okay. So here, pay attention to what the difference is going to be. Look where the mirror is, the object and everything. My slide is stuck. Oh, the struggle is real. Okay, here it is. New situation. All I did is so let's figure out first where are the images. First, it's supposed to draw. So I'm going to go approximately there, like that. This is just approximate. When you guys are doing a ray diagram for a lab, let's say, or if you're doing a ray diagram for a test or an exam, use a ruler, use a protractor, make this perfect. You don't want to get the wrong answer because you're just approximating. So there's my step 1, draw my image. Step 2, draw the reflected rays from the image to the observer. Yeah. And step 3, work your way backwards to find the incident ray. However, there's a problem here. What's the problem? It's not hitting the mirror, right? The mirror is not in the right spot for me to see that image. So does this observer see the object in that mirror? No. So in this case, observer cannot see the image. So my next question to you is, what can the observer see? What's the field of vision of the observer? Okay, I'm going to change colors for this. Giving me issues. It'll be the same color. So yeah, okay. So the question is, what's the field of vision? So this observer, he can see or she can see all the reflected rays coming from this mirror, including the endpoint, the beginning point, and the end point, and everything in between. So remember what I said when we were talking about an object that's aligned, the most important points are the extreme points. So let's figure out what those are. So if I had an incident ray hitting there, coming into the eye, so I can draw that reflected ray here. It'll go like this. I'm going to erase this other stuff. No longer relevant. We're okay with that? So from the edge of the mirror into the observer, like that. From the other edge of the mirror to the observer, that. Yeah. And what I have here is the same situation where I have a reflected ray and an incident ray, right? So I could work my way backwards, find my incident rays. And I could even extend these for for the rest of the page, basically. And what do you notice? Can I see the object? No, in this case, I confirm that I cannot, right? And this observer can see anything between these two incident rays here, right? So any ray coming from here, I can see. So if an object was, for example, right here, I would not be able to see I wouldn't be able to see it, right? Because it's outside of my range. I can see anything in between these two incident rays. So I can see anything in this kind of zone here, right? And so if I have an object on the outside or on the bottom, on the top of this object here and this object here, I can't see them. They're not in my field of vision. If I had an object in between, can I see this object? Can I see that one? Yeah, it's in my field of vision. It's in my field of vision. Okay? Yeah. Well, yeah, I guess if the observer just looked over there straight without using a mirror, yeah. But what if there was like a barrier right here? Then you can't see it. You might need to look around a corner, for example, to see something with a mirror. So you can't see that part of the room on the other side. All right. Any questions on field of vision? Good. All right. Is this still all review? Some of you have done this. All right. Okay. Next question. Next question has to do with two mirrors. All right. And how is that possible to draw an image with two mirrors? So let's go with it. There's this one object. This time I drew it as a dot. You don't have to worry about two dots and having to connect them. But this object is going to get an image in this mirror. So we can use the trick and go at the same distance to the mirror on the opposite side. I have an image there. But there is another mirror, so I can create another image too, right? I have this mirror here. So I have to go on this side, same distance, all the way over here somehow. So that's about here, I would say. Both of these are images of that one object. Now here's the tricky part. If I'm looking in this mirror here, there is one object that I have an image for, and that's this object here. There is another object. What's the other object in this? If I look in this mirror, there's another thing that is going to get reflected. Yeah, exactly. This mirror is also going to get reflected, right? So not only is there this mirror, not only is there a reflection of this image of this object, is also a reflection of this object. This object is a two-dimensional, like one line kind of thing, but it's easy to do because it's perpendicular. So what it's going to look like is this. Like that, right? And if you look at this mirror, you're going to see a reflection of that mirror, of this other mirror. So you're going to have another reflection here. Amen. And now if you're looking into the mirror, right? If you're looking into this mirror, for example, you can see this mirror, you can see this object, but you can also see this object slash image forming another image in the virtual image mirror to make another image. I can see that. So there is another image right here. So imagine you're looking inside a mirror, and in the mirror there is a mirror, and in that mirror there's the reflection of that last object. If I were to look at That's me looking at this mirror. If I were to look at this mirror, then I would see this mirror reflecting that object. So what would be the reflection of this object here? Would it create a different one, or would it be the same one there? It's the same one, right? Just because of the way the angles of the mirror are placed. This image is going to, the image of this object, because now that's an object in this mirror, this image is going to be formed right there on the same spot as that. Okay? That was our step one. We drew the image, just there's three of them. All right. What I want you guys to do now is maybe use a pencil, because we'll go over this afterwards, or you can use the walls. I have a lot of markers here. And what I want you guys to do is draw a ray diagram for how you would see, how the observer would see this image. Right? So you can ignore these two. We don't ignore them, but I don't want you to draw ray diagrams for these ones. I want you to draw a ray diagram for this. So if you're looking at this image, what are the rays going to do? Okay? Do that, so I'll give you guys 10 minutes to try to work on it. Yeah, but that doesn't mean anything. You can even go directly on the whiteboard if you want. If you don't want to redraw, you can even go here, Max. how do you see that? How do the rays do whatever they need to do for you to see that?
The one top of
Yeah. Well, start with the straight line. No, that's the first step, right? Start with straight line. And figure out.
This guy goes à ce moment-là, à gauche, le bloc qui est bas, il est trop fort. Tu t'en vas vers le bloc. Tu sais, quand tu prends l'avion, oh, it should keep to the
Not sure?
no, very sure.
Explain to me. Very sure. Yeah, explain. More you said.
This image is reflected by this image. It starts from those, because those are the object of this.
Okay.
And this one is the object of those.
Okay, so how did you say? So let me tell me
Maybe
where you
this
started.
one
What was your
doesn't
step
work.
one?
This one I'm not.
Top left to be observed.
Okay. Okay.
That's what we're observing.
Okay.
After it goes to, not sure.
Well, it starts from that one because this is the image for this object. Okay. But this is the image for this object.
So
And then there's only that one with.
Okay, maybe I'll increase your confidence level by telling you that your answer is correct.
everywhere.
Everyone. Now you just have explain it.
There's only that one that I'm not entirely sure.
Here is because when you do the reflected line, after you process to go back to your object.
Okay.
After here, the reflected line is here for this object. So after you go back to your initial object.
So what you're missing, what would be perfect there for you, is if everywhere that, sorry, everywhere that your rays hit a mirror, a real mirror, draw a normal line, figure out the angle, right?
The angles like the actual values.
No, I mean, in reality,
Okay,
but is this diagram? You guys figure it out? Yeah, keep working. Started off well with that clear one. That would be the first step. Yeah. And so from there, we can do it every time the ray goes up here, but it's a fiber long, but it's a real mirror.
Non, je sais pas. Ben, combien de temps que c'est ça? Les deux autres méthodes sont aussi les gars qui ont vomi au départ.
Ah ouais?
C'est Zach Maillancourt. Le gars du première. Puis il y a Laure aussi. Ouais.
Ah ouais?
Non. Quoi? Sa mère joue. Ah ouais?
Mon mentor était pareil.
Hein?
C'est l'ancienne designer de sa compagnie de mentor. Genre de vêtements.
Tu connais la compagnie?
Indienne.
Ah ouais. Ok. C'est pour ça que là, à cause de Mini Cooper.
La mère encore était propriétaire. Ça avec un autre. Yo, c'est. La graphiste est tellement stackle. T'as-tu vu? Comment elle se stackle, ça fait ça?
Ça va être ça, cash, cash.
Silver Edition. C'est tellement dense. Ça paraît qu'elle est tellement vieille. C'est vraiment les meilleures calculatrices. Je vais aller dans un programme avec des maths.
Je suis jaloux. Bon, c'est vrai que c'est cool.
Les boutons sont brillants.
Ben oui.
Je me demande, do you want to change?
C'est ça.
Toi, tu vas t'inscrire en quoi à l'université? Dans un an?
Software engineering.
C'est qui a dit ça?
C'est moi qui sais.
Je t'ai exposé la semaine passée. La question.
Ça se peut, ça peut se faire. Donc,
Architecte du droit.
toi qui as la tête à ça.
À quoi?
Architecte.
All right,
Mais
Au revoir.
let's see, please.
Architecte, ça.
Okay. You're not actually dying. Okay, hope you feel better. Make sure you catch up to this, okay? All right, so let's go over some of this. I told a couple of you guys this, but I just want to make sure that everyone's on the same page. What your first step is going to be is always to draw, sorry, after this. You always start with the image that you're looking at. In this case, I told you that this is the image that you're looking at. Always start by drawing the line directly from the image to the observer, to your eyes, to whomever is looking at anything. So like that. Ideally, this should be straight. And again, the observer has eyes. And the eyes never shoot out beams unless you're looking at someone else's eyes. The observer is observing. The rays are always entering the observer's eyes. Okay? And every time that ray hits a mirror, you have to apply the law of reflection. So it hits a mirror right there, let's apply the law of reflection. So I'm going to draw a normal line. All right, what's going on here? All right, there's my normal line. And I have some angle here that I'm going to reproduce on the other side of it. Like that. And I work my way back. It just so happens that if I did this correctly, it's going to go up to this image here, and that's not a coincidence. But look, I hit another mirror, so I should draw another normal one. Every time I hit a mirror, a real mirror, draw a normal one. That's why the law of reflection. That means it's going to be on the other side here. Oh, check it out. It went right on the object. That's also not a coincidence. So this angle is the same as this one. This angle is the same as this one. I'm going to point to some rays, and you guys tell me if it's incident or reflected. All right? So this one here. This one is going to be both because it's reflected from this one, but incident to this one. Okay? Right. If I were to give you any other angled mirror, right, you always follow the same rules. As long as they're flat mirrors, you can always follow these rules, okay? Straight from the image, then follow, work your way backwards until you get to the object. Okay? How many images were formed here? 3. If I had a 60-degree mirror, right? If I had my two mirrors at 60 degrees, let's just say it's 60, and I have an object there. How many images is it going to form? A lot. More or less than 3? More. And if I have, oh yeah, how about this? How about when you're in one of those changing rooms and there's a mirror on each side of you? How many images are there? An infinite number, all right. And so that means the more the mirrors get parallel to each other, the closer they get to being parallel to each other, the more images are going to be formed. So this, you know, automatically it's going to be more than that. But how many? 360 degrees divided by 60 degrees is equal to minus, well, it doesn't matter if it's plus or minus, but let's say this. What's the ratio here? 6. Yeah, am I going to get 6 images? Let's see if it works for this one here. Well, you just said 360 divided by 6.
Yeah, but.
All right, so, oh, it's a 360 over 60 minus 60. Oh, okay, I thought I meant like divided by minus. Yeah, I get you. Here it's 390, sorry, 90 degrees, right? So it's 360 degrees minus 90 is equal to 4. So there's only 3 images, right? So we have to use minus 1. In fact, the way it works is, imagine there was a full circle and you separate them into a quadrant. How many quadrants do I have on this circle? 4. One of the quadrants is occupied by non-mirror space. And that's that one that you have to subtract. All right, so in this case, it'd be 360 minus 1. It's going to give you 5. So there's 5 images created if I have it. Now, if I had a 0-degree difference, 0-degree angle between my two mirrors, well, then you kind of get the impression that you have how many images? What's the limit as x tends to 0? How you write it? Infinite. What's infinity minus 1? Okay. Right, so that's why when you have two mirrors that are parallel to each other, mathematically, you have a theoretical infinite number of images being produced. Right? Any questions on that? I'm just going to write that equation here so that people who are absent can get it. Nope, that's not the thing. My erase is not working. There you go. The number of images. Okay. Perfect. Let's move on. So now we saw double mirrors, and you can do any number of double mirrors that you want. Let's look at double lenses. Double lenses. The situation I have for you here is I have an observer who's watching this, and the location of the observer is incredibly important. Would you put an observer here? Ever? Why or why not? Right now, the observer is on that side. Here I have, by the way, what kind of lenses are these? Convergent, otherwise known as biconvex lenses. All right, the question was, Shani, why would you not want an observer here, or why would you want an observer here? Right, it's like, there is no, I mean, there is going to be an image, but I don't really care about that image because I'm on this side of the, there's nothing, there's no lens between my eye and the object. So I'm just looking at the naked object, right? So if, may I use your glasses, Max? there's no point in having glasses if Max puts them over here and looks at the front table, right? If she's looking at that, right, she can't see anything because her glasses are all the way over there. Right? There's no interference. The lens has to be between the observer and the object. Okay? Thank you very much. Right. So it's really, really important that the observers understand this is going to determine the time convention of the things. Really. So here's a trick that you guys are going to use when there's double lenses, right? You kind of ignore them. You ignore one and you just work on the other one until that one's done. And which one is the light going to hit first? F1 or F2? Yeah, the light's coming in this direction, right? It's emanating from the object, right? And it's going to hit this lens first. So let's ignore this altogether. Let's ignore F2 altogether and draw the ray diagram for F1 as we know how to do it. So do you guys remember what the three rays are? You're doing one of these curved lenses problems. What were they again? Yeah, that's the first one. Parallel through the focal point. Yeah, through the focal point and parallel. Reflected, that's for curved mirrors, but this is for lenses. So it'd be right through, just right through, straight right through to the middle of the lens. All right, so let's do that. All right, perfect. So there are my three rays. They all meet at one spot, and I get an image. The image is right there. Yeah. All right, we have some calculations to do now. All right, so I want to figure out what the distance is between this lens and my image that I just fitted. Again, I'm still ignoring F2. I haven't even considered it. So I'm looking for the distance from the original lens. What formula I need to use? Well, that's the only formula we have. So 1 over F is equal to DO plus 1 over DI. Okay. Yeah. The focal length is given to me. My original distance of the object is given to me, and that's 50 centimeters. So let's just plug everything in. 1 over 20 minus 1 over 50 is going to give me 1 over DI, and DI, you guys are going to tell me what that number is. Can anyone do this in their head? 1 over 20 minus 1 over 50? Give it a try. Don't succumb to the need of a calculator. What's the common denominator for these two fractions? Would be 1 over 0. So what would that be? Hold on, let's look at this. Common denominator here is 100, right? You multiply this by 5, you multiply this by 2. So 5 minus 2 is going to be 3 over 100, but you have to flip it, so it's going to be 100 over 3. Yeah, 33.2. I didn't change any of the units. I left everything in centimeters. My answer is perfect. So my object formed 33 centimeters away from this lens. That distance is 33.3 centimeters. This other lens is located at 25 centimeters. And 33 is further than 25. So I actually drew it correctly. That's where it's supposed to be, beyond that lens. What's the distance from this lens? How far is this distance here, this new DO. It's going to be 8.33 centimeters, right? However, is it on the right side now? Do I want my object to be on this side of the lens? No. So this is new to you guys. You're going to consider that as a negative object distance. Okay, it's not 8.33. It's going to be negative 8.3 because it's on the wrong side of the lens. And the focal point here is 10 centimeters. So the focal point is actually like right there. If I were to press it in a relative location, that would be where the focal point is. And when you have a lens and you have an object within the focal length, what is it going to do to that object? Is it going to make it smaller or make it bigger? We talked about this last class. Let me go back a little bit. If you had a magnifying glass, you guys know what a magnifying glass is? Put a magnifying glass, and I just held it like this. Would I see anything bigger? Or would everything, it wouldn't be virtual, but everything would be upside down and arguably smaller and not in focus. However, a magnifying glass works really well when you bring the magnifying glass close to the object. In fact, what you need to do is put the object between the magnifying glass and the focus point. And then it makes it clear, right? And that's the exact same situation here. I have my magnifying glass, and my object is closer than the focal point. So is my image of this new object going to be bigger or smaller? Bigger, right? Remember, when you put it in front of the focal point, it's gonna feel bigger. So I'm not going to draw the ray diagram because it's going to be very, very messy, but you know how to do that. Exactly what we did. But we can calculate it really easily. So let's do that. So this is 1 over F2. What's that? We're going to find out. Yeah. So 1 over F2 is equal to 1 over DO2, which is that new location, plus 1 over DI2. That. So 1 over 10 will be equal to 1 over negative 8.3 plus 1 over di. Call that di. Give me a number for di. I don't know if this one can be done in mental math. If you can, that's amazing. I cannot do this. 8.33, what is that? You guys do it. And tell me if you get the same answer. 8 so that is 5 over 3. 1 over 10. 3. 3. Is it a number less than 1? Maybe my math is wrong. What did you guys get? How much? What was the number you guys got? 4.54? Okay. Positive or negative? What happened here? So we got a positive. Now, is that a virtual image or a real image? That's a real image. It's positive. Okay. Perfect. That's going to be our distance. And which side of this lens is it going to be on? Which side of the lens? Left or right? And the right side. Right? Because that's where they're supposed to be. You're going to have a, sorry, that's not where this was. If it was a real image, it would have happened on the opposite side of the lens, but it's not going to happen here. So it's going to look like this. And it's going to be enlarged. And that's what the observer is going to see. The observer is going to see, what, the other way around? Yeah. The observer is going to see this image here. And it's going to be inverted. Yeah. So in mirror, it's different from in mirrors. In mirrors, you want them to be on the same side. So if I were to you want to know what here's that. Let's see if this one works. This one's good. All right. Erase this. Let's say you have this object. We're ignoring the double lens situation. You have this one object. It's going to, we're going to draw the rays, maybe like that. To the focal point. The focal point is there. There. So far, so good. Do the lens. Do the focal point. Parallel. There. Okay. Those are my three important rays. And I have to work backwards to find their image. So my image is there, right? They're real or virtual? Virtual, right? So in lenses, when the image is on the same side as the object, it's considered to be virtual, right? So it's going to be, and so this object, is it real or virtual? Real, because it's a positive number. So if DO is positive here, and the image on the same side is going to give me a DI that's negative, right? What's important is that they're the opposite signs to each other. Okay, so when they're on the same side, the signs of the DI and DO have to be an opposite sign. Okay, it would have been positive if it were on this side, but it's not supposed to be here, so we gave it a not supposed to be there. We give it a negative sign. Okay, so that means here the object is the smaller arrow. We consider that to be a negative DO, and if the DI is on the same side, then it has to be the opposite sign to it. What was your second question? No. And later on, when we go upstairs to make the telescopes, you'll see that when you have two lenses, you're not going to produce an upright image. Glasses will not totally flip it before you see it. Glasses converge and diverge, but not, they're so close that there isn't enough time for it to flip. So it doesn't flip the image for you. Just like, oh, actually, here's a good example. Look, they're so close to the lens that it didn't flip the image. It kept it the same orientation. Think about it. If you have an eyeball and a lens, right? So if you wanted to see a flip image, this is what would have to happen. The flip actually has to happen before it. But what ends up happening, this is not reality. This is not reality. This is reality. You have an eye, and you're looking at this. What this does is this. Okay? So your brain flips. Otherwise, it would flip, and then your brain would flip it again, and you would see it upside down. Here, your brain is the only one that's flipping. Did you see it right side up? We actually have a lesson, tomorrow's lesson is going to be all on eye disorder. We're going to talk. Okay, so perfect. In this case, we have a larger object inverted, and we can see it. This is basically what a telescope is. I'm going to get into a bit more detail. Is that a question? Reflected? There is no reflection happening here. The refracted rays, you mean? It's going to be really, really messy. I'll try my best. Let me erase the other ones. Is that okay with you? So I'm going to tell you that the focal point is this tiny dot here because it's supposed to be at 10 centimeters and my object is at 8 centimeters. So the first one is parallel through the focal point and through the center and then through the focal point and parallel. Yeah. So I'll have to work my way backwards to find out where these meet. So they're going to meet somewhere like there. And I did not draw this correctly, so you're not going to get the right proportions, but that's what it's supposed to be. Okay, I'm done with this. Can you guys pull out PowerPoint 12? We're quickly going to go over a couple things, and then we'll go upstairs to build a telescope. Okay, so PowerPoint 12, please. Okay. So we're getting into this area where we're going to manipulate light. All right, so we found out how light is used and how lenses can be used to bend light. But now mankind or whatever, we became smart and we want to use this to our advantage. It's not important to us to have this inverted thing at like 1.1 magnification or whatever. But actually, we need to use it for something. Here it is, the manifestation of something. Telescope. It's a very rudimentary telescope. It's not very good at all. And the reason for that is because of what we call a refractive telescope. A refractive telescope is basically just two lenses, all right? And while it's good at magnifying things, it's not really good at resolving. I'm talking about resolution. But the idea is that if I wanted to see something, like if I want to see what's across the street and I want to see it bigger, imagine you take a 5 kilobyte image on your computer and you just zoom in. Are you going to see anything any better? Not necessarily, because the resolution is not that great. It's the same idea with your eyes. Your eyes have a certain resolution. So just because I have a really amazing telescope doesn't mean I'm going to be able to see things better, right? It's still going to be somewhat unresolvable. We have better telescopes that are not refractive telescopes. They're mirror or compound telescopes. We'll get into a little bit of that, but the use of what do you call it? Of reflection and refraction. Yeah, like Hubble. That's a compound telescope. Yeah. Notice here. What do you notice about the shape of this telescope here? Yeah, it expands. It flares up. So it starts narrow and gets bigger. Right? And that's the major concept behind telescopes. Imagine you have a light funnel, right? And this is the funnel that we're talking about. So all the light that's getting entered in here is going to, through lenses, focus them and then make them enter your eye, and then you get to see all the light enter in here. A really good telescope would look like what? Would it be narrower or wider? It would be much wider. Then you want it to be super duper wide so you can capture a whole bunch of light and therefore see a much clearer image because you get more light information. So if this was way bigger, then you'd have a much better telescope, and that's problematic because this is already pretty expensive. It's like $300 for something like this, and it's not. This is like an amateur's telescope. Someone who's a hobbyist who might go to the countryside and look at the stars. This is what they might have. But if you want to really study the universe, you really need to capture a lot more. So you have the Hubble telescope, which is this gigantic, like has multiple meters of radius for the main lens or for the main capture. And the reason for that is because it captures all the light. However, that's kind of hard because imagine building a lens the size of this room. How the heck are you going to do that? It's going to be super duper expensive. Not even like we're talking about like billions of dollars expensive, and even then, the chances of it breaking are super super high. You have to transport it, and then it breaks, and then you have to pay for it again and fix it and whatnot. So that's why the idea of mirrors is actually much more used in big telescopes. What you essentially do is you create using concrete a big flat surface or big curved surface, and then you paint it with reflective material, or you coat it with reflective material, right? So you can create a really gigantic mirror, not necessarily manufacture it. That's why a lot of the bigger telescopes, even the one in the International Space Station, is going to use that technology of mirrors and things like that. But we're going to start off simple, and we're going to talk about regular um, refractive telescope. And a refractive telescope is made up of two lenses. All right, the objective lens and the eyepiece. Which one is the one that you look through? Eyepiece, because it goes on your eye, right? Um, the objective lens is going to be the one that's going to look at the object, so that's why it's objective. The eyepiece is the one that goes on the eye, so that's the one that's closest to your eye. So again, we're going to talk about these refractive telescopes, and that's this first main. There's one concept that I need to talk to you guys about. I have an object that's really, really far away. When we're looking at using a telescope, we're not looking at something that's really close. We're pretty much always looking at something that's far, right or wrong. You use it to spy on your neighbors, it's still pretty far, right? And you use it to look at the moon, far. Look at stars even further. So let's understand what this far object means. So here it is. Here's my object in front of a lens, right? This is not a far distance. This is a very close distance. And so the air rays come like that. This one refracts this way. This one goes right through. This one refracts this way. We kind of get an image. This is in the object is really close. The things in space are not close. So let's redraw this and make it really, really, really far. Can I have a better marker? Who had the good marker here? You? Can you guys see that lens there? It's really crappy. Is that you trolling me? You're the wrong one. Okay, I got one now. All right, so there's my lens there, and my object all the way here. So I have my three rays that I need to draw. Right, so here it is. The first one is going to be parallel. Next one is through the center. Right. And the next one is through the focal point. Right. So What you notice about these is that their incoming angle is more and more similar to each other, right? So these look like kind of parallel. Not really by theory, but in practice, they're kind of parallel. And this object's not even that far. This object is 4 meters far from the lens. When you're looking at the sun, I was looking at the sun with the telescope. You're looking at other stars. Um, those rays coming in are all parallel. Okay. So if you're to look at all rays that are coming in parallel, what's the rule about lines that are parallel to the lens? They turn to the focal point. Exactly. So the rays come to the focal point no matter what. So far, so good. So all parallel rays end up on the focal point. When you're looking at distant objects, all the rays are parallel, so all the rays end up on the focal point. Has anyone ever burned anything with a magnifying glass? It's like a typical 5-year-old boy who knows not supposed to do this, and they do it. You've done it before? Yeah. So what ends up happening is you end up taking all the solar rays that are coming from a very far distance and focusing them onto the focal point. And that focal point is the focus of all those rays. And so it becomes really hot and it burns things, right? If I had a really gigantic magnifying glass, would it burn things hotter or just the same amount of hotness? Hotter, because I'm focusing way more rays, right? And the reason why you're able to focus them all onto that one point is because the sun is so far away. If I were to take one of these lights and try to focus it, you'll see with a magnifying glass, it's not going to work. You're always going to get a really big focus area, a big light area. You're never going to be able to get a dot like you're supposed to do with the sun, for example, when you're using a magnifying glass. All right. So we know now this concept that light comes into the lens parallel when you're looking at faraway objects, right? And what happens is it's going to hit the lens, the objective lens, because that's the one that's closest to the object, and it's going to focus on the focal point, and then it's going to, that image on the focal point is going to create another image for which the eyepiece is going to enlarge, all right? So essentially, we'll be doing the math on this, not today, next class. Essentially what's happening is this lens, this objective lens, is bringing the object close by making an image right there. And then the eyepiece is going to take that image and blow it up so that you can see it. Okay, that's exactly what a telescope is doing. That's as simple as it gets. I mean, really, like it's ingenious how we figure this out, but it really works, and you guys will see it when we get upstairs. The trick, though, is that you want this point to be the focal length of both lenses. Okay, because here, if they're all focusing in on the focal length, that means you've represented this big object, which is a star or the sky or whatever. You represented this big thing as a tiny dot. And because it's so close to the focal length, and we said that when you're close to the focal length, the lenses blow them up, right? So that means now that it's close to this lens with a smaller focal length, it's going to make it much, much, much bigger, right? So then you can see the details of it. That's what we're going to do upstairs. So when we get there, what I want you to consider is this: the ideal magnification. I think I have the equation here. We're going to get through this later. Here, the ideal magnification is equal to the objective focal length versus divided by the eyepiece focal length. So you want the biggest magnification possible. So that means you have to use the biggest objective focal length possible and the smallest eyepiece focal length possible. All right, so you're gonna have to choose your lenses upstairs. Make sure you choose it such that it optimizes your magnification. Second important thing is that you want to make sure that your lens meets at their focal length meet somewhere in the middle. Okay. So if this one has a 25 centimeter focal length and this one has a 5 centimeter focal length, how far apart do you want them to be? So you want their focal lengths to be the same spot. That's what you want. So if this one has a 25, this one has a 5, how far do you want them to be from each other? 30, exactly. 25 plus 5. So it's going to be 25 until here, 5 until here, So the distance between them is 30. Okay. You also want this to be kind of flexible because you're not going to be able to produce it. That's why when you see like those pirate movies or whatever, they have a telescope that they move. When they have a telescope, they do this with a telescope. That's because they're adjusting the length of the two lenses so that you can get the perfect image. Not everyone's eye is the same. Not every lens is perfect. You can do it theoretically, but it might not be good in practice. So you'll have to make it somewhat flexible when you go upstairs. When you build the telescope. Okay? That means you want your lens and your two lenses to be mobile. All right. I'm going to give you guys tubes. You guys know what to do with it. You can ask me questions. It's going to be in groups of 2, and you're not handing anything in other than showing me that you have a picture that you took with your cell phone through the telescope to say that you've done it. Once you show it to me, you can go. You can. I'm going to go there straight now. If you want to take a break and then come, you can do that. Or you can go straight up and do it so that you can move faster. It's up to you. So that's what we're going to do now. Okay? In groups of 2, please. In the physics lab.